Ron Brandt. He's been featured in a recent issue of the Extraordinary Science magazine in the October, November, December 1994 issue. He has a 10-pound, 10-horsepower motor, and he told me a little earlier today that he was born in the state of ignorance and has never left, which is actually a very good position for a scientist to be in. It's the ones who think they know everything who can't learn anything. So Ron is a good researcher. He began building motors and radios back in the 3rd grade, and then he started taking trips to the junkyards and collected all the parts he could from even steering columns from wrecked Model Ts, and his father called him a scavenger. This was back in the early 30s in Trout Lake, Washington, near the base of Mount Adams. And he made a lot of sophisticated motors and unusual electrical devices during that time. He joined the Navy. He became an instructor in math and electronics, and he was also mingling with people who were involved in the famous Philadelphia experiment. This really sparked his curiosity into electronics. He spent 35 years working for the International Brotherhood of Electrical Workers, and he also did a lot of experiments during that time with his motors. He built his first electric car in the 70s, converted a 66 Dodge Dart with a 24-volt, 32-horsepower starter generator off a B-52 bomber that went into that Dodge Dart. So that was a pretty interesting little project. And he's also designed and built several other fascinating circuits which have been presented to our conferences before. So let's give a warm welcome to Ron Brandt.
Doggone, you didn't talk long enough.
Don't worry, you'll have plenty to say.
I got a few comments to make here before we start on this motor. I've got some theories that I would like to express. If everybody that's working on anything, I don't care what type of improvement, what kind of energy improvement, as long as it cleans up the environment, I'll do what I can to help them. First of all, we haven't got much time. At the rate we're destroying this planet we live on, I would like to think before I leave that there's hope that my grandchildren might grow up, have some air to breathe. And everybody's going to have to get into the act. Put their egos aside, and remember there ain't no luggage racks on hearses. And we'll get the job done. And it don't make any difference who does the job, as long as it gets done. And a lot of things have been held up by government. A lot of it's been held up by egos that want to make more money and control everything worldwide, this or worldwide that. Well, we're at the point now where we don't have that luxury to control it all for one person or for one company or another. I think that if everything went to market today that is feasible, that's working, it would take 20 years with everybody putting everything they had into the act. It would take 20 years to turn the destruction of our planet around. And by that time, Standard Oil is going to run out of oil anyhow, so they shouldn't be worrying by then, or what else, in that respect. So when we had the gas shortage back in '73, I figured, well, it's time. I had built motors, I'd seen what could be done, and I wanted to get it going, and I figured, well, at the price of gasoline, $1.50 a gallon, it was there for a while, maybe people will take a look at electric power. So I built one. The only problem was the gas shortage ended, and the price of gas went back down to 49 cents, and so nobody give a damn. They didn't care how much air, how much oxygen they destroyed with the gasoline and the diesel fuel. But if you stop and think, If you're driving a car with 400 cubic inches and it's turning 3,000 revolutions a minute, there's 400 cubic inches times 4,000 going into that engine. And it don't make any difference whether you're burning clean fuel or dirty fuel. You have destroyed more oxygen in 1 hour than you'll breathe in a month. 1 hour driving your car will consume and destroy the oxygen, regardless of how clean your engine's running. That what came out the exhaust pipe is not breathable for human consumption anymore. It has to be rejuvenated and reprocessed. So we have to think about this in a standpoint of reality. The other reality is the World Health Organization 10 years ago, well actually almost 13 years ago now, took oxygen level tests on people in isolated communities where the population was fairly stable. They went back 10 years later and took the same people in the same communities and found that there was a 10% drop in oxygen in the blood from what it was 10 years earlier. At that rate, the metamorphic diseases, the molds, the fungi, are going to be killing us all off in the next 5 or 6 years if it continues to drop at that rate. We're an oxygen-based organism, and we have to have oxygen to live. No matter how you figure it, we've got to have at least a fair supply of oxygen. And now we're getting down, like in Portland, at 3 o'clock in the afternoon, they done an oxygen test downtown Portland, 14% oxygen. At 14%, we haven't got enough. You wonder why people are shooting at each other and why they're ramming each other's cars and everything, because they're running out of oxygen. They can't think straight no more when they get down that low. Anyhow, so much for my talking. I designed this motor to try to be as efficient as possible, in that the motors I bought, like the 32 horse motor I got for the car, is a conventional DC motor with brushes, has field coils, has windings on the armature. And it looked to me like, why should I take half of the electricity and create a field, and then the other half to create another field to fight it? Why not take a fixed field that we got in the magnets, set it up so the magnets are in a permanent state of keepership, and then use electricity to induce the magnets to move to another place? In other words, make one piece of metal a little less attractive than the next. Now that's a little bit loud. This is what's in that motor, just an identical duplicate to this, only it has 16 magnets. Each one of those magnets on a straight lift will pick up almost a 100-pound piece of steel. There's a lot of torque involved in the magnets. There's only 5 thousandths clearance between the magnet and the stator. Now this is just one piece of stator. There's 1.5 inch stack in there, and what power I put in only makes one segment a little less attractive than the one that's not getting any power. So the motor turns. Oh, I guess it would help if I turned the power on. Now, we got infinite speed control, any speed we want. We got instantaneous reverse, anytime we want to reverse it. And it will reverse at 6,000 RPM, but if it isn't bolted down, it'll jump up in the air 6 feet. I know, I had a neighbor come in and I had it running at 6,000 and he flipped the switch accidentally and the motor was up in the air and I catching the motor with it running and trying to shut this down at the same time. It wasn't funny. Anyhow, with this design, there's no brushes in the motor. There's only 2 things in there to wear out. and that's the two bearings. The bearings I put in there cost $7.90 a piece, and they're 10,000-hour bearings. Now, in a car, how far would you drive in 10,000 hours? The motor is designed so the bearings are easy to replace without having to get into the working parts of the motor. It's not that technical. I tried to make the old saying, keep it simple, stupid. Well, I tried to make it as simple as possible. Ease of maintenance and maximum efficiency. And there may be better motors. And I can improve on this. This is my first prototype. I made a mistake in this one. I wanted 49 slots in here. And the draftsman, or the computer guy that's done my CAD work for me, he marked on the print 49 slots. I didn't count them. I faxed it off to Lamonics, and Lamonics made me 48 slots. And that's why it growls. If the 49 slots would be in there, it would be as smooth as could be. So that's an error that's only there, and I own up to the mistake because I didn't count the slots. Now, let's see here. Now this is on 50 volts for division. I'll bring this down to the line. And we're putting in about 80 volts now that it's showing there. This line here is hooked across a 002 shunt. And I'm set on 20 millivolts per division. And so that is indicating the amperage is going into the motor. Now, we'll turn this over here a little bit. Now you can see the little pulses I'm putting in. Very small amount of amperage I'm putting in. I'm getting as much back. We'll put this on 0. Get it as accurate as possible for the perfectionist. Now, these pulses that are going in are very short in duration. These back EMF pulses down here are wider, actually, than the forward EMF pulses. Everything below the line, I'm capturing in these condensers here to use in the next pulse, so that I don't need to take quite so much electricity out of the battery. Now, this motor is equally as good a generator as it is a motor. Now, I'm going to shut the power off going in. And you'll notice a sine wave, but the sine wave, as it slows down, collapses. And we're just hooked on to one phase of the three-phase. I have here a three-phase bridge rectifier that's taking and snubbing the motor. Actually, if I take that off, I'll have 1,000 more RPM, and I'll have real long down here. But that runs the risk of burning out my transistors, so I keep it snubbed down a little bit. Find a quiet speed so we can talk. find a quiet speed so we can talk. But I designed this basically for electric cars because of the torque. The torque is unlimited in instantaneous torque. It's there. I have run it long term for heating tests. I had a party that said, oh, if you put the power into that seal, see, it's sealed, airtight, no dust, no magnetic filings, nothing can get in there. And I didn't have the shroud on it, and I didn't have a fan on it. I run it without any cooling, with 2100 watts going in for 4 hours, and it was still cold. It does not heat. But it looks nice with the cover on there, and it keeps something from bumping my Hall effect switches on the back that control this. In the finished product, it would be built a little bit neater than that. As I say, this is a first-time prototype. I have the designs over here for a 50 and 100 horse motor that will be 13 inches in diameter and 5 inches thick on a 50. On a 100 horse, it'll be 10 inches thick and still 13 inches in diameter. Here's a picture of the stator. You'll notice there's a very small amount of iron. I keep the iron to a minimum because 2 reasons. I've done extensive research on the saturation time of iron and how fast it will give me back the energy that I pushed into it. So the less iron I can use and still have the iron, to get high torque you have to have some iron. An ironless motor, I've got ironless motors at home, have no iron at all. They run beautifully, they're very efficient, and but they're not a high torque motor. They're like third horse, quarter horse, and they will work very nicely at that rate. But if I tried to go to a car motor, I have to have some iron to get the torque. And to increase the speed, I reduce the iron to the minimum so that I don't waste energy. Anytime that you're going to shove energy into a piece of iron and you have to put more energy in it than is necessary, you're wasting something. And the other thing that I looked at in working in the Navy with submarines and all the different types of electronics, some of it was secret at the time. Anytime that you can take X number of watts and make it do 2 jobs for you at the same time, getting from point A to point Z, and it does 2 jobs on its way there, you're coming out ahead. But if it only you take so much and do 1 job, and then you take so much more and do another job, when you can make the same supposed electrons do double work at the same time. So that's why I tried to make it as efficient as possible, get the mileage on electric cars up to 200 miles. I don't know how many people here that have contemplated buying electric cars, but the people that I've talked to say that if they have a trustworthy 200-mile range, they would think very seriously about it. I honestly think that we can give them 200 to 400 miles on a battery charge, depending on the types of batteries. We have many different types of batteries coming on the market. I'm working with just this conventional lead-acid deep cycle batteries, and I think that we can get 200 plus. There's a couple of innovations in this. The next one will be more efficient than this one. The next one to build. The 50 horse there is designed for very simple construction. If I want 100 horse, I take the same stator, wound left hand, and it goes in the same motor. All the parts are universally designed so I can have a 50, I can have 100, or I can go to a 200. using the same starter plate. I don't have to make a multitude of different sizes, like this design here. I can wind this to get 10 horsepower. But if you want a horse and a half, why, boy, we can make it super efficient at a horse and a half, same size frame and everything. And it's not any bigger, and it's not as heavy as a conventional horse and a half if you went and bought one. So we don't have to have so many different models, having every one of them different. And as I hate to see waste, and when I have rewound this motor at least a dozen times to do tests to see, like I can wind it for 12 volts and it'll turn 6,000 RPM on 12 volts. If I put 24 volts on it with the same winding, it'll turn 10,000. And I have run it over 12 several times. The RPM, the way it's designed, it's not going to fly apart. I took it to Portland and put it on a dynamometer, and I got up to 3,500 RPM, and I'm going to kick it up a little higher. Oh, no, it'll blow up, it'll blow up. And I says, I've turned it 10,000, it ain't going to blow up. I finally found out that his dynamometer would have blowed up. He didn't want me to turn my motor any faster, but I knew that 10,000 wasn't going to hurt it. And so then he conceded that he didn't want to blow up the dynamometer. But the horsepower rating goes up very fast when you start getting into the higher RPMs. The low RPM motor is a energy hog, in that when we're designing for efficiency, it's awfully hard to get the efficiency that we can get if we go to higher RPM. It's awfully hard to get efficiency if we don't go to high frequency. Now, what I would like to do with this design is I'll go to 3,000 kilocycles. See, I'm running to 1,500 kilocycles now. I'd like to go to 3,000, or somewhere between 3,000 and 50,000, maybe even 60,000 kilocycles, because my recovered power will increase. My efficiency level increase. I went up to 20,000 and it increased it, but I blowed out transistors. They said they were rated at 20,000, so I'm going to run them up to rating. Well, I found out that they don't perform so well where they rated them. They rated them at the blowout point. And so I had to drop it back down to 15 kilocycles to get the longevity. But we have now, I designed this 3 years ago, we have now MOSFETs, high amperage MOSFETs, that will go to 1 megacycle. And there is what I'm going to do in my next controllers, is use MOSFETs, 200 to 300 amp MOSFETs that will go up to a megacycle. Then I can play with the efficiency range to get it right on the 100% mark. I don't want to go over 100% because it seems like people have an aversion to anything being over 100%, so we're going to make it 100%. And if we've got here, now this is the starter plate like I was showing you here, only this is the 49 slot. And the iron, where in that one I had the iron coming into here, I cut back on the iron because I found out I didn't need quite so much. I could get by with less iron between here and here and still had stability. I think we got a cross section there of this motor, and also one of the 50 horse. Now that's a cross section there of this motor here. There we go, by George. Now, something that a lot of people don't know. I spent a considerable amount of time building Ecklinators. I invested $20,000 into John Ecklin's, I called it his folly. It was his dream. And John Ecklin was a brilliant man. He was a theorist. He never built the motor. We built it. It did not function quite like he thought it would. And I give him credit for being a good, sincere person. But he never built one that worked. And there was a lot of us, not only me, but a number of other people, put a lot of money into Ecklinators. But I went a little farther. I got Hall effect switches, I got XY recorders, and I plotted the magnetic fields in the iron. What happens when this charge goes in? What happens when the power comes off? And we made charts and more charts. And we found out that the magnetic field doesn't quite behave like everybody thought it did. Depending on the kind of iron you use, you can alter the behavior of it. We found that we could bounce magnetic fields off of magnetic fields, and they would expand and contract this way at the same time. And so we learned a little bit from it. So I don't dislike a gentleman that was working with me. He says, we wasted a lot of money. And I said, well, look at it another way. If we went to college for 8 years and paid the tuition and everything to learn these things, we would have wasted a whole lot more. So we're paying for our education. And we're learning the hard way, but we learned. And this is an Ecklinator here, one that we had running under its own power. And by the rules of engagement, so to speak, if you drop the windage and you drop the bearing drag and everything, it was over efficient. But when I put a battery charger on it to charge the battery that was running it, I could not light a flashlight bulb and maintain the voltage on the battery. In other words, that's how close to efficient it was. In 4 hours, we dropped 1/100th of a volt on the battery in 4 hours running. So it was getting damn close to efficient. But according to the friend that was working with me, oh, it's over efficient. We're 112. And I said, when that sucker will burn a light bulb sitting out there on a table with nothing going to it and the battery will not go down, then I'll say we have done it. That's my theory. Of course, I'm a little bit dumb on these things, but I like to see something that's marketable that you can take home and count on working. Anyhow, after we quit trying to do it Ecklin's way, I took all this investment and we looked at it and done some experiments with resonance, and took that same amount of iron, same rotor, and we was able to put it into resonance, and damn near killed me because it put out 30,000 volts at 3 amps. But I like to see something that's marketable that you can take home and count on working. Anyhow, after we quit trying to do it Ecklin's way, I took all this investment and we looked at it and done some experiments with resonance, and took that same amount of iron, same rotor, and we was able to put it into resonance, and damn near killed me because it put out 30,000 volts at 3 amps coming out of that little generator. and it jumped about 8 inches, hit me on the arm, blowed this arm up like a ballpark frank, and I landed on the floor. I mean, I'm not kidding you a bit. This wrist and hand was just stretched like a balloon. It boiled the blood instantly. I thought maybe I'd lost my arm for a little bit, but I checked the nerves, and the nerves were still alive, so in about half an hour to an hour, all the swelling went back down. But I had a sore here where it jumped and hit me on the elbow, came out my fingers. So I had some respect for it. And then I tried to figure out how to use this to make energy units for motorhomes, RVs, or people that live out in the boondocks where there is no power, and make it safe so it isn't going to kill somebody. And even if I could make money on something, if it's not safe, I won't play with it. I won't let somebody have it. If anybody's going to get killed, it's going to be me, because it won't hurt me. But I had to go to the power company and buy a power line transformer so I could cut this 30,000 volts down to 118 volts so I could use it. And the frequency was running a little over 900 cycles per second, so it wasn't, when I tried to get it down to 60 cycles, I couldn't maintain resonance. The iron, I used M19 in that, and the balance of iron, I could not get it to resonate at 60 cycles, go into resonance and stay there. And so I've got it sitting under my bench in the shop. And someday, when I have more time and money than I got common sense, I'll probably play with it again. And some soul in essence, I would like to see everybody get on the ball and do what they can to get somewhere. And a lot of people are in the same boat I am. I invested a lot of money into Eklund's deal. I put a lot of money into this, and then I had people that wanted me to do work for them, and they sent me checks, and they were made out of rubber, and I got them in the safe. They bounce like a ball, but I figured someday I might get some rubberized acrylic and put these checks in that so I can use them for paperweights and bounce them off the wall when I haven't got anything else to do. Anyhow, so much for being funny. That's my weird sense of humor. Anyhow, getting back to the motor. I took a 37 kilowatt Kato generator that had a 60 horsepower diesel engine driving it. I took the diesel engine off and had them haul it to the scrapyard because it had thrown a rod through the side. I only bought it because I wanted the generator in the first place. And the Kato generator, for those of you that don't know a Kato generator, they are a brushless generator, one of the best type generators built for industrial use. The beggar's that big around and that long, and it puts out 37 kilowatts of 440 three-phase or 220 three-phase or 118 three-phase. I can get any voltage I want, and it's all three-phase. And the reason I bought it is so that I could put a motor like this on it, and I could have three-phase power for my milling machines and everything, because the power company doesn't have three-phase power available where I was at. I'll be honest why I bought the generator. But it made a good test load for this when the gentleman that I was dealing with at the time wanted to know if it would get hot, how much power I could put in it, and what temperature rise. So I put the temperature gauges on it, and I loaded it, and I let it run. And it never got any warmer in my hand in 4 hours of running. And I think that I can see right down the eye of that camera, and this is trying to blind me there. I was just being funny. I think it's we ought to take a little break here, and then we'll come back and answer what questions we can. You know, I'm normally not a talker, and it's awfully hard to try to get everything said that answer as many questions as might come up as I can. I like to build things, but I don't like to talk about them very much. There's something I'll mention here. Now, this ammeter is only reading the power that it takes to turn those transistors, and it's drawing over a half an amp just to turn the transistors off and on. The motor is only drawing about an amp. If I take this half an amp off of what's going to the motor, then the motor is drawing less than an amp to sit there and run. And we'll shut this intensity down. Questions asked. Well, we didn't get it on tape there so that people could remember it. One gentleman asked me why it didn't have very much torque the way it was running here. Because I set it on torque control, and it's got a small amount of torque. I can stop it. It doesn't draw any more current from the battery for me holding it there than it does while it's running, because I've got it set for that. Now, and it's still set for torque control. I can slow it down to a lower RPM. See, now it slows down easy, see? But that's on torque control. Depends on how much torque. If I want 5 pounds of torque, it'll put out 5 pounds. That was one question that was asked. Now we'll quiet you down so that people can hear and I can hear. I can't think of the other questions that was asked. Go ahead, sir.
I'm curious as to why you had 49 segments rather than 48, as 48 is a multiple of 3, which would seem like that would be fitting for a 3-phase motor.
Well, see, that's an illusion. If you have never built a motor, if you've never examined a motor generator, you will find that you always have an odd number against an even number, because if you put an even against an even, you're going to have this growl. If you want a quiet running motor, you have to have an odd running against an even. And that's just the rules of the game. In this, when I put it together and found that I had 48 slots, and the magnets, I had already put the magnets on the rotor.
How many magnets are on the rotor?
There's 16.
16.
Just like those that you've seen here. And I couldn't turn this with an 18-inch pipe wrench, because it stayed right at the ones, they were lined up perfectly, and it did not want to turn. But when I put power on it, it would take off like gangbusters, and you couldn't slow it down or it would stop. And because it was even and noisy, you couldn't stand to be in a room with it. So I took the magnets loose, and I done a mathematical calibration, and I made up for the missing slot by spacing the magnets to salvage my $2,700 investment in the stator plates. That's what they cost me, and they were wrong. That was my mistake, because I didn't count what the guy put on the deal. It was marked 49 slots, and when Laserdyne got it, they used the photograph to make the deal instead of counting the slots. Now,
if anybody wants to ask a question, if you come up here, it'd be a heck of a lot easier, okay?
that way the questions and the answers would get on the tape that other people will look at, and their questions may be answered. So any questions that you think of that somebody else that wasn't here might want to know, Go ahead.
You mentioned for an electrical car that you could increase the range of that electric car from, let's say, 60 miles with your motor. We could go as high as 200. How can you do that if you're only maybe showing a 5% improvement? Let's say a alternating current electric motor is 95% efficient. What do you do to make this dramatic jump in range with the same in your motor?
Could you, by any chance, find a conventional motor that's 95% efficient? You can't find one. They don't make them 95% efficient. They run in between 68 and 75. And so you have a loss there. It depends on the manufacturer. Some of them do a little better than others.
Right.
But the conventional motor is not efficient. And the more efficient motors are permanent magnet motors because you don't have to create the field. And so you get more efficiency. And there's a number of permanent magnet motors being built that are using commutators. There's a few that are experimenting with a similar situation that I'm doing. And they're going to get a little bit more efficient. But there's not very many of them in cars yet. So we're going to have to work on the efficiency. Now, something that I did is I went to a larger diameter. I increased my torque arm and squared my horsepower by increasing the torque arm. And so in this 100 horse or 50 horse that we had there, the 36 magnets and 109 slots will bring it up to 50 horse. And if I put 2 stators in the same rotor, I got 100 horse. And so we use leverage to increase torque. I've seen a experiment that I've done myself with a 2-inch long arm, and the amount of energy it takes to swing it is cut down almost 90% on the power that it takes to produce the same torque. If you go bigger in diameter, it takes less energy to make these magnets go because you've got leverage. It's just like you putting a pry bar under your car and lifting it up with one finger, and without the pry bar, you're going to break your back trying to lift it up. Same principle involved.
You mentioned that this was worked equally as well as a generator. Now, that would imply that when you want to stop your car, you should be able to reverse the process and take some of that momentum you put into it and put it back in your battery. Is that correct?
Okay, now that's something that's why this 3-phase bridge rectifier is here. If you want to go down a long hill with this in your car, you just pull it into passing gear and you don't have to use the brakes, and it will be charging your batteries all the way down the hill.
So that should extend your life of your batteries
that
there.
will extend. In other words, you're going up a hill, you draw extra current to go up. With this, the way I've got it designed, you should recover at least 2/3 of the energy going up this hill if you go back down the other side the same amount.
Can you actually use it, say, stop and go traffic? Can you use it to as a braking?
You can use it as a braking. I had braking. This chip in here has braking in it. Only I had to unhook it because I had people that would hit the brake on it when it was running at too high a speed and it generated too much current. I didn't have the feedback at that time set up to go in here. But there is the capability in this chip I've got here for instantaneous braking.
Right, so that could be engineered into
Yes,
it as part of the car.
and the chip will do it. The only thing is that I tried to design this so that the little old lady from Pasadena that wants to buy an electric car, it goes on an automatic transmission, works better on an automatic than a straight stick. You can get in the car and drive it just like gasoline. You have the same control ability as the gas engine, and the only thing is that if I put it in the car, I have to, if it's going to do its automatic braking, then I'm going to have to put a switch on the throttle, so when you take your foot off the throttle, it kicks it back into the charge mode.
Right.
The
Thank you.
yeah.
what was your decision to make the magnets on the stator rather than the rotor?
The magnets are on the rotor.
On the little piece you have up there, the magnets are on the outside.
That is the rotor.
Oh, I see. Oh, okay, I get it.
See,
Thank you.
this piece here is stationary. It is bolted on to 4 stainless steel non-magnetic bolts.
Power motor, and
This never moves. You remember there's no brushes in here. The wires are in these slots, and so this couldn't move. This is the heart. That's what rotates. Centrifugal force can't tear it apart. This is chromoly tubing that it was made out of, and it has very little expansion. So I don't have to worry about it disintegrating, I don't think. This is the heart. That's what rotates. Centrifugal force can't tear it apart. This is chromoly tubing that it was made out of, and it has very little expansion. So I don't have to worry about it disintegrating from speed, I don't think. It may be interesting someday to run it up, increase the RPM till the point up. But I'm very confident that 20,000 RPM wouldn't hurt it. Go ahead.
Yeah, Ron, how did you fasten the magnets to your cylinder?
Okay, in fastening magnets, there is a company, I'm trying to think the name of it, makes a bonding agent especially designed for this. The bonding agent you cannot get them off. Once I put them on, there's only one way to get them off. And right now, what's in the motor now, I use 350 degree bonding agent. And the magnets are good for 600 degrees before they lose their magnetism. So I can take and put it in my milling machine, and I got a hook deal that hooks onto the magnet, and I can take my torch and I can warm the outside and the magnet will slip. And it doesn't heat it enough to hurt the magnet. But I have also got the bonding agent that will not release till it gets to 600 degrees, so if it ever got hot enough to release the magnets wouldn't have any magnetism anyhow.
Okay.
And that's oh shoot, I'm trying to think of the name of the company that makes that, a bonding agent. It comes in a spray can. You spray this blue stuff on, and you let that dry, and then you put this other stuff on the magnet, and you have the guide set up, because once that magnet hits, you'll never move it again without heating it up to get it loose.
Is the magnet contoured to the cylinder itself?
Yes. The magnet is contoured to match the cylinder radius.
Okay. Now the next question, what were you doing when you got this 30,000 volt kickback in your arm? Was it from this machine or some other machine you were working on?
That was from an Ecklinator, another machine altogether that I worked on to prove Mr. Ecklin's theories. And when we give up on his theories, and I used, being I had the product there, I done some experimenting, and I wound a couple 2,000 turn coils, one on each side. Because in my experimenting with magnetic fluxes, I found that they had an atomic weight. And if you move them fast enough, they stretch out. So I figured, well, if they got an atomic weight, then I should be able to collide them together head on, south pole against a south pole. So I put 2,000 turns here and 2,000 turns here, and I pulsed that beggar, and they hit, and my load coil was right in the middle of the collision zone. And I only had 130 turns of wire. How I got 30,000 volts out of 130 turns of wire is strange. But when it hit resonance, it did it. But otherwise, it didn't. But when I put the right condenser on and got it into resonance, that sucker flat put out the power. Now, without it being in resonance, it put out 3 amps at about 105 volts, spinning it with another motor. But when it hit resonance, then it went up to 3 amps at 30,000 volts. The amperage stayed the same. Apparently, the mass in the iron controls the amperage, because that's the only thing that didn't change. The mass of the iron represented 3 amps. But the voltage went up from just under 110 to 30,000 volts, but it still had the same amps.
This is an interesting concept that most people don't comprehend. Is your motor here, can you resonate that at frequency like the Eklund motor?
No, this I didn't design in that respect, because I designed this for a variable speed car motor. And if you're going to work with resonance, you're going to have something that has a constant capacitance and reluctance to make it resonant, or inductance. And when you change the RPM, you're going to change the required capacitance. And so it would be kind of hard to make that resonate. Besides that, the coils in there, there are not really any coils in there. So the coils wouldn't want to resonate very well. I can wind it with coils. Say if I wanted to make that into a 2-horse motor, I could put some coils in there that would draw less current than these can draw, and make it a smaller motor, and then it would be very efficient as a 2-horse motor. But I designed this for high torque to move a vehicle from a standing start out into traffic. And that, in working with this design, it's primarily, my motive was to get high instant torque when I needed it, and high efficiency the rest of the time.
I have one more question. When you put the Kato 37 kilowatt Kato generator on your system here, what output could you expect out of that 37 kilowatt unit?
Well, I loaded it to a specified wattage input here, and I had 5 100-watt bulbs burning on the Kato. But the Kato took, with a Dayton 2-horse motor, would not run it, wouldn't turn it with no load. It went 30 amps on a Dayton 2-horse to turn it the same RPM as I was turning it with this, and the Dayton kept kicking out the circuit breaker in the motor because it wouldn't handle 30 amps. So then I put this on, and then I loaded the generator on top of it. And when I was running it with the Dayton motor, I didn't even have it excited, because the fan inside of it's that big around. And it sounds like a jet engine sitting there running with without it even being excited. So then I excited it with this. I loaded it so that I could get over 2,000 watts in, because I figured that if I put 2,000 watts inside that little compartment, if it's going to heat, it's going to do it pretty quickly. But it didn't heat. So then I knew that my back EMF was pulling the heat out. Pulling it out with the back EMF, and that's why it didn't heat. It tells you right quick, because when you're throwing energy in there, it's going to make heat if you don't pull it back. And that's why the back EMF circuits are here and everything, is to keep that temperature down.
Is there such a thing as a ratio between your electromotive force going in to your back EMF that you recapture? Do you have any thoughts there?
Well, the frequency, I can determine how much I'm going to get back with how I increase or decrease the frequency of this controller. I can get more back and make it more efficient with higher frequencies. If I go to lower frequencies, it will get a little less back EMF. In other words, each pulse, you're going to get the same back EMF, but if you've got so much off time between that and the next pulse, then in other words, you're getting X number of pulses per minute, and the more of them I can get back on the back EMF side, the more energy I have recovered, and the cooler it's going to run.
Wish you well in your conversion to your 200 amp MOSFET circuits and your progress in the motor.
I think we've just about covered it there, haven't we?
Ron, I got a quick one for you. Can you run the motor for us one more time? And one other quick question is, do you have anything documented on the motor yet that we can get a hold of?
Well, I could send you the dynamometer deal where it went off the scale, and when they wouldn't let me run it any higher speed, so I didn't really get to the maximum on it. That's all I've gotten outside of my own notes for what I've done, and of course very few people like to trust the inventor's notes.
So basically you don't have anything really published as of yet that we can sort of go into building one of these things?
No. Everybody that wants to build a motor can take my thoughts and what I have done and try any other innovation. You may do better. Who knows?
All right, how do we get
Or
a hold
you
of
may
you?
do worse.
How do we get a hold of you?
Anybody that wants to get a hold of me can contact Steve or JW here, or I hate to have I don't have a phone of my own, and I've got all of my equipment parked in my sister's yard, and I have an extension on their phone, so I would rather not have too much unless it's important information. I will give the numbers. 503. But unless it's important, I don't want to tie up their phone, and I can't afford making very many phone calls myself.
Just one question. Does your stator internal of the rotor give you more leverage?
Well, that's part of the reason that I put the rotor on the outside, because it increased my torque arm. And it give me the inertia in the rotor because of the larger diameter.
I'd like to thank you for being so frank and telling it the way it is. You're an unusual man, and I wish you the best.
I thank you very kindly, sir. Now, he said I was frank, so his name must be Ernest. Now, somebody asked me to run the motor again, so I run it again. And it has a definite little sing of its own. But right now it's turning at about 3,800 RPM, because I have it wound at the present time to run up to 200 volts. And at 200 volts, it'll go over 6,000 RPM right now.
Ron?
Yeah.
What horsepower did you say this motor was here?
I designed it for 10. We checked it on a pony brake horsepower to a stall, and it stalled at 27. So
That's pretty good.
the torque is there. And that's what I was designing for, was to get that quick torque for a car. I mean, if you want to move out into traffic, you don't want to sit there and have somebody ram you. You want to be able to move for a few seconds. That's why it's designed for that. And it will draw, for those few seconds, it will draw a humongous amount of power. That's why these transistors are 300 amp, 600 volt capacity, to give you that when you need it. But when you're driving, you won't be using it. You won't be drawing very much current.
Just a real quick one. The
The signal that you're using, is it a pulse width modulated signal?
I have, the brain in here has a pulse width modulator, and then I got another little brain in there that is a speed sensor.
Could you apply the same technology for the conditioning the back EMF back into your condensers for driving solenoids and so on?
Well, it seems that the back EMF comes back at just about the speed of light. And I'm lucky to catch it to keep it from damaging the transistors. So I put it in the condensers and reuse it. Now, there's other innovations that we can do. But this is as far as I got, and my capital was gone, and I'm not going to spend any more money till I either win the lottery or something on that order.
There's a specific design problem that I to you about regarding using a PWM signal to drive a linear actuator, where I'd like to keep the heat down. It's an under-hood application, automotive technology, and I don't have a whole lot of temperature rise available to be able to drive this device.
Well, you want to keep the heat down.
Exactly.
Well, that's something I think we were trying to wind up here. Let's talk about it after we wind this up.
Through the Tesla Society, and just address it to you and we'll get it to you.
That would work the best. Anything in writing or anything, or any questions that they can't answer, they'll either get a hold of me or something on that order, because I am going to be moving as soon as I can find a place to park my equipment, as that becomes a necessity. See, Monday I didn't know whether I was going to get here. My mother had Alzheimer's, and I've been taking care of her by myself. My wife passed away 3 years ago, and she went like off the deep end Monday, and she didn't know me. First she thought I was my dad, and then she thought I was my stepdad, and she was mad at both of them, so she was mad at me, and I had to put her in a rest home Monday. At 7 o'clock Monday I got the paperwork done, and I left at 8 o'clock Tuesday morning to get here for this. So I've got...
A few things to take care of.
I had a few things to take care of. Now I got to worry about finding a place to set up shop and a building to start working in, because I've got all of my equipment loaded into two 20-foot vans, and not much way to work until I get a place to do it.
Thank you very much for trying it.